Hi there, this is Jacob Nash, and this will be a review of Unit 2 of Basic Calculus, any kind of calculus, first calculus that you might take. So this unit is mostly about derivatives, so let's review what that even is, okay? Well, first of all, remember in the last unit, I'm not sure if I made a video on this or not, so I apologize if I didn't, but we talked about how you can have something that looks like this. So what would this actually mean right here? Well, believe it or not, this is actually a different way of writing a rate of change. And, you know, right now, for the time being, I'm not going to get into the specifics of how this gets into this form, but this actually starts out as a change in y over change in x. And we know that that is slope. But for this purpose, we're actually talking about where h approaches 0. And what is h? When we're talking about h, that's going to be a distance from a particular x that we're talking about. And if that doesn't make sense, basically this limit that we have right here is something that tells us the slope of a curve at a point. So what would that mean, a slope of a curve at a point? So let's say this is our curve. This is our point. What is the slope at that point? And this is exactly what a derivative is, in case you forgot or just don't know. That's exactly what a derivative is. It's the slope of the function, the graph, at a certain point. And this isn't the way that we usually represent derivatives. As you may know, we usually might do f prime of x and then we'll use our derivative rules, but you just have to keep in mind that occasionally you might have to use this format to calculate a derivative. And it's not that hard. You would just simply take whatever the function is and then plug it in. And I'm not going to do that in this video because this is just supposed to be a review, but just keep in mind that you would want to know how to do that. So now we're going to talk about, or actually let me bring up one more thing for that first point. So you very well could get a question where it tells you something like this. Like, let's just say, okay, why isn't it drawing? Sorry. Sometimes I still don't know how to use this thing, even though I've used it for like years. But so let's say you got a question and it was like, okay, here's your function right here. Find the derivative of this thing and then also the equation of the tangent line. So what does that mean? Well, the derivative, if we're finding that just tells us the slope of a curve at any point, right? That's what I said before. But if it's also asking for the tangent line, we have to have a specific line that will tell us exactly what that line is. And a tangent line, if this is our graph once again, then tangent line is something, even though it doesn't look like it, it only touches it at one point. So it's saying, what is that line? How would you go about solving that? Well, let's say that it wanted us to use this limit thing instead of just our derivative rules that you probably know. All you have to do is you're going to plug it into that graph. So this is our f of x, right? So then our f of x minus h, all we have to do right there is just do this, x minus h, plug that into that part right there. And then you would just plug it in and solve, and you would eventually get your answer. Then what you have to do next is use the point slope formula. This is something that you just definitely will want to know. Okay? And what you would get from what I just said, that would be your m. Okay, so you would get your derivative from plugging these two things into that. Let me just zoom out so you can see it all. If you plug these two things into this, or you just use your other derivative rules that we're going to review later, then you would have to plug in, it would have to tell you the point, it would give you the point. So let's say the tangent line at 1, 3, it would have to tell you something like that. Then you just plug in 1 into whatever you get from this. Once again, this is just supposed to be reviewed. That's why I'm not really actually doing it. But you would plug this x value into whatever you get from there, whatever the derivative is. And the answer you get ends up being the m that's right here. And then the y1 and the x1, they are just these values right here, and then you would rearrange it to get your line. So that's what you might have to do, so just saying. I can make a specific video about that if you'd like to see it. I might have already, honestly, I can't remember. But sorry about that if that didn't make sense, but I can't spend too much time on one thing because there's so many things to go over. Differentiability. So if something is, a good way to abbreviate things, it's good to abbreviate things sometimes. We're just going to say diffable. If it's differentiable, what would that mean? Well, the slope from the left must equal the slope from the right. So we'll just say this. The slope from the left must equal the slope from the right. So I'll show you an example of where that is the case. There you go. It would be right there. I don't know why it's doing that I don't know what kind of stupid setting I've turned on where it's changing what I draw into shapes, but a situation where this is not the case is something like this. Like, at this point, that's going to be a kind of a problem right there. Then you can't have vertical tangent lines either. So if I had something like this, that's not differentiable, and it's not going to be possible for what we know to take the derivative only at this part right here. Another thing is that we can't have corners or cusps, so this is going to be a problem. That's called a corner. And then that's going to be a problem too, where it's like kind of curvy at a part. That's called a cusp. That's also not differentiable. Anything else that just looks normal, it is differentiable. And then another thing that's important is, if it is differentiable, it must be continuous. The other way around is not necessarily true, because this is continuous, is it not? But it's not differentiable. And then you have to think of the contrary. If it's not continuous, then it couldn't be differentiable. If it is continuous, like I said, it's not necessarily differentiable. So that's all I have to say for that. Now, this topic 3 is going to have like the majority of the video. We're just going to talk about all the derivatives that you just need to know. Before we start, let's remember that we can represent the derivative with many things. So we can say f prime of x. We can use that limit thing that I already showed you. We can also say y prime, or anything prime. And we can also say dy dx. That would be if it was in terms of y. If it's something else, you could do dr dx or whatever letter it is. But there's many ways of doing it, and they'll try to use different ones to mess you up, to make you confused, but if you see any of those, they are the same thing. Okay, so let's talk about the different basic derivatives. So if I take the derivative, and when I do derivatives, I'm usually going to say d dx. If I take the derivative of c, well, I have to tell you what c is, and I'm saying that c is a constant. If you don't remember what that means it's just a number, any number. If it's not something that has a variable in it, if it's just a number, the derivative of that always equals 0. Now that might seem pretty straightforward, right? But they will try to confuse you sometimes by doing something like this. They'll say, what is the derivative of e? And automatically you might think of the function e to the x, but this is trying to trick you because e is actually just a number that's approximately 2.71. It's a constant, therefore the derivative of it has to be 0. You could also, another one they'll try to throw at you is pi. A lot of people, when they see pi, they get confused for a second. They end up thinking about trigonometric derivatives, but don't worry, that's just a number, 3.14 approximately, and the derivative of it by itself is 0. So, and then any number, like 6, 1, any number, is going to be 0. So that's an important one. All right, the next one we'll do is, what if you had a constant times a function? So we'll just say constant times a function, we'll just call that function f of x. Well, we're going to have the constant still beside it with just a derivative of the function. So that doesn't always make sense to people because it's abstract. So let's actually choose a function. And let's actually choose a constant, so it makes sense. We'll just say 5x squared. And I haven't talked about yet about what happens with the squared, but this is going to end up being, I'll just make it so it's easier for you to tell, 5 times the derivative of the function. So our function is x squared. The derivative of that is 2x. We'll talk about y in a second. But the point is, the 5 ends up beside it, and then yes, you could multiply that to get 10x. So that's the point. If you have a number multiplied by it, then it's fine. But you just need to remember, if you have it added or subtracted, that just goes away. So we're just going to have 0 plus 2x, or just 2x. So only if it's multiplied by it does it matter, or divided, would it stay the same. But if it's added or subtracted with a function, then it just goes to 0. And then if we add or subtract two functions that really should say f of x, g of x, but I'm just putting that for now, then you simply will just add or subtract the derivatives. So that's pretty straightforward. But as you may know, if you're reviewing, that's not the same for multiplication and division. So if we have multiplication, so let's say we have a function times a function, unfortunately you can't just do this. That's not how it is. You have to do something that we call the product rule. So I'll just write that down here. The product rule. And the product rule is fg prime plus f prime g. And of course, some people might have it in a different order. It doesn't matter, commutative property doesn't matter what order you do it. But you basically are just doing the two combinations. We're doing the normal times the derivative of the other times the other derivative times the normal of the other thing. So you're adding those two parts together. So what it's a very good strategy to do is to just put off to the side, what are these four things? And I'm going to be like, the first thing I see is f, the second thing I see is g, and then you take the derivatives of both, and then you just plug it into that formula. And that's the product rule. It gets easier the more you do it. Now, one that's a little bit more annoying is the quotient rule. If you have f divided by g, derivative of those, unfortunately, is not just that. That's not how simple it is. We have to use the quotient rule, which is super annoying in my opinion. Quotient rule. And the quotient rule is a good way to remember it. I didn't come up with this, by the way. Is low d high minus high d low divided by g squared, and off we go. Like I said, I didn't come up with that. But that's a really good way to remember that, because otherwise it's kind of hard to remember. So we're saying low d high, so we're saying the lower thing, g, times the derivative of the high thing, minus high d low, so it's like the reverse, divided by g squared, not divided by g prime squared, just g squared. And off we go. So that's the quotient rule. That's what you'd have to do. And for just like I said for the product rule, I'd just go ahead and write off these four things to the side. It's not going to hurt anything. just to make it a little easier on you, just what is the high thing, what is the low thing, and what are the derivatives of them both? And then you just plug it into that formula. So that's the quotient rule. Pretty annoying, right? But we still got a lot of derivatives left to go. Next, we'll do the power rule. That's not that bad. So if we have a function x to the n, we can say, okay, nx to the n minus 1. And I know I hate things like this, right? Because it's kind of just stupid. I'd rather see an actual example. Well, let's go back to that x squared that we did earlier. How come it's 2x? Well, you just put the exponent beside it. So we have 2x, and then you do the exponent minus 1. So we have 2 minus 1, which is just 1 or just nothing there. So that's why it's 2x. Just to give you another example, what if we had 4x to the 7th? We'll put that to the side, and we can actually just multiply those together using what we know about constants beside a function. So that's going to be 28x to the 6th. We just subtract 1 from the exponent. And it could get a little trickier. There's some that they try to throw at you, like this. The power rule still applies, because this actually is x to the 1/2. So we can just say 1/2 x, and then we'll have to do 1/2 minus 1. I always just make common denominator, which is going to be negative 1/2. And then, you know, what else might they do? They could be really dumb and decide to do something like this. What if they do that? Well, that's actually just going to be x to the negative 4/5. So we put the negative 4/5 beside it. We do 4/5 minus 5/5, which is just 1. We get minus 9/5. So that's how the power rule works. All right, moving on to the next thing. All right, now we're going to see something called chain rule. And once again, it will look stupid when I write it, but I'll give an example so it makes sense. But you need to know the technical way of describing it too. So this is the technical way of doing it. So if we have a function within a function, then we end up saying this. And I'll explain what it means in a second, because it might not make sense just by looking at it. So this means that we do the derivative of the outside thing, but we leave the inside thing the same. That's really important. See this? G of x, it's the exact same as it is here. You don't do a thing to it. But then you multiply it by the derivative of whatever's in there. So let's give an example here. How about, it's kind of hard to think of an example without stepping into another rule that we haven't reviewed yet, but I just will. So let's say we had sine of 4x cubed, okay? We have to use chain rule. Here's what some people might do. And that's incorrect. That's just a common mistake. We're going to talk about in a second later that the derivative of sine is going to be cosine. And then you might just do the derivative inside, but that's not how we do it. Because remember, I say you leave the inside thing alone at first. So it's actually going to be like, keep that the same for now. But then you multiply it by the derivative of what's in there. So we're going to be like, okay, now we'll do this. And this is the correct answer. And the chain rule can apply to so many types of functions. It can also apply to something like this. E to the, that's a good example, kind of. We do the derivative of the whole thing, and that's just going to be this. And yeah, once again, I stepped into another rule that we haven't learned yet. But that's how it is for E things. It's always just going to be the same thing as it is. So that's the derivative of x times the derivative of this thing that we left alone. Now we have this, using our power rule. So that's how the chain rule works. And chain rule, product rule, those are the two, at least for me, that are easy to just like not do, and then you'll get it wrong. Now let's talk about what I just mentioned. the derivative of e to the x is actually just the same. And that's kind of a funny thing. The value e, which I said is about 2.71, is a very significant value that relates to derivatives. I'm not going to get into that right now. That's higher up math than what I know, but that's the truth. Just to tell you, this e is very the actual name of it is known as Euler's number, and it is, well, I was wrong actually, about 2.72. That's the correct thing to say. And this means that anything e is actually just going to be the same thing, but you might have to use chain rule, like we already mentioned. Oh, shoot. We'll keep this the same, and then you multiply it by the derivative of the thing that's there. So, but that's the bottom line. It's the derivative of that thing is going to be the same thing, but you might have to multiply it using chain rule if there's something other than x as the exponent. Now, what if we have something b to the x, where b is just any number, so like 4 to the x or something? Well, what you have to do is you can say, okay, yay, but not so fast. You actually have to also multiply it by ln of b. So if we had 4 to the x, yay, it's the derivative of that is going to be, just pretend there's a d dx there, 4 to the x times ln of 4. Not too bad, right? It's like the same as e to the x, except for you have to do ln of that. And technically that is the same thing as what you do for e to the x. We're actually still doing that. We're saying e to the x times ln of e, but this is actually equal to 1, so that's why we just only say that. All right, so that's what it is if it's something like that. So I'm just trying to show you like all the possible things. That's why this is going to take a long time. But now what if we have ln of x? That's just going to be 1 over x. Yay, simple enough, right? So if we have ln of x plus 2, we're going to say this. The derivative of ln x plus 2 is just 1 over x plus 2. Now you might be wondering, well, what is the derivative of 1 over x? Well, 1 over x is actually x to the negative 1 power, so it's going to be negative x to the negative 2 using our power rule. So if you see something that you're like, I never learned how to do the derivative of that, change it into something that's what you know. So I don't know about denominators, but I do know about exponents, so just change it to an exponent. Now, of course, you might be wondering, or maybe not, but what about log? So if you have log b, where b is the base of x, that's going to be similar to the ln of x. So we have 1 divided by x, except for you have to multiply that by ln of the base. So if I had just log x, it's actually going to be this. And you might say, why 10? Well, it's understood if there's nothing there, it's a 10. That's just one of the things in math that are good to know. So if I had a 9, then I'd put a 9. That's pretty simple, right? All right, and now we get into our trigonometric ones. These are going to be kind of annoying, but you just have to memorize them, unfortunately. If we have, oops, I'm still on eraser. If we have sine of x, and just remember there are 6. So we have sine, cosine, tangent, and then the inverses of those, cosecant, secant, cotangent. The derivative of sine of x is cosine of x. Just remember you would have to use chain rule if there was something other than x in there. The derivative of cosine of x is negative sine x. The derivative of tangent x is secant squared x. And if you really wonder why it turns out to be like that, there is a way to find that out, but at least for my purposes, just memorize them. It doesn't matter if you know why. That might not be true for every class, but at least for what I do. So just memorize them. Secant squared x. Now, of course, we have to get into the dumb ones. Cosecant x. Now, this is very strange to some people, but it's actually going to be negative cosecant x times tangent of x. So that's why people might be like, huh, how does it end up with the same thing? That's just the way that it works. Don't forget the negative. And I'll tell you a little cheat in a second. Secant of x is actually going to be secant x times tangent x. And then the last one is going to be cotangent x, and it is negative cosecant squared x. Now here's the little cheat. Cosine, cosecant, cotangent, those all begin in C. All of those always have negative derivatives. That's a little way that you can help to not forget your negatives. So those C's have the negative, and then the other ones, sine, secant, and tangent, they're positive. Now, sadly, you also need to know 6 more, which are the arcs. So what do I mean by that? So here's something that's pretty important to remember. This, what would that equal? That's going to be 1 over sine of x, and that's also what we call cosecant of x, right? But there's another thing that can happen that is different. We can have this -1 here, and that doesn't actually mean the same thing. That's not a mathematical operation. That is actually just going to be what we call arc sine. So if you see these two things, that's actually the exact same thing. And if you remember back to geometry, that's what we would have to do if, like, let's say we were trying to find an angle or something. To get that by itself, we would do that. That's like the opposite operation. We would sine to the -1. And that's not the right way to say it, but these two things mean the same thing if you see them. But you have to know all of these for all 6 of them. So let's get going. So for these arcs, we have arc sine, cosine, tangent, arc cosecant, arc secant, and arc cotangent. Just like with the normal ones, these 3 are negative, and then these 3 are positive. And then I'll circle the 2 that actually look kind of similar to each other. These end up looking similar, these and these. So we almost have like 3 types. And let me show you what I mean. So let's say we have this, which also is the same thing as arc sine. It's going to be something that looks a little bit not super fun. It's just got to memorize it. 1 over the square root of 1 minus x squared. Little hint, for all 6 of the, that's not true. For all of these top 4 right here, it's always going to be a negative in there. So that's what arc sine is. Now I said that cosine, arc cosine looks kind of similar. Hey, guess what? There you go. That's the only thing that's different. Just make it negative, because I said the C's are negative. So those are the exact same except for sine, arc sine positive, arc cosine negative. Next, let's do arc cosecant. Arc cosecant is a little bit different than this, okay? Instead, we have x squared minus 1. Once again, I said it's always minus. We have to put a x beside it too. And arc cosecant, since it begins with a C, it's negative. And I said secant looks similar to it. Arc secant is the same, but it's positive. Because the S, sine, secant, tangent, always positive. So those look similar. Now the last 2, which in my opinion are actually the easiest to memorize how they are, is arctangent and arccotangent. So arctangent is 1 over 1 plus x squared. So these are the only ones where there's a plus. Tangent, arctangent, and arccotangent. So arctangent equals, the derivative of arctangent equals 1 over 1 plus x squared. And then the derivative of arccotangent is the same but negative, because once again, the c's are negative. So that's just a way to remember it. We know that there's 3 possibilities of how they could look. So these are the 3 groups, and all of the derivatives of those will look similar, but the blue ones are positive and the yellow ones are negative. So unfortunately, those 12 trigonometric derivatives you will have to memorize. Goodbye, we're done with that now. And let's see, that's it. That's all the derivatives that you have to know. So I told you that was going to be a long section. This one, not as long, although it still is a little bit tricky, but not that bad, not that bad. Implicit differentiation. So implicit differentiation is something that we have to do when we have multiple variables, and it's also something we have to do for related rates, and we're going to talk about that later. But sometimes our things that we have to take derivatives of aren't going to be as simple as this, right? Essentially, when we take the derivative of this, we're always going to get a y prime right there, and we're going to get over here, this part, it's a constant, so it's 0. This part, right here, the exponent is 1. We put that over here. 2 times 1 is still 2. And then 1 minus 1 exponent is 0. So that's actually just going to be 2. So now you might just wonder, why is there a prime here and not here? Well, we would be assuming that we're doing ddx. So the dd something, let's talk about that for a second. So when we're saying ddx, we are taking the derivative with respect to x. It doesn't always end up that way. We could do ddy, we could do ddz, we could do dd anything that we feel like it. And when there's a difference in variables, that's what we have to do for implicit differentiation. So let's look at an example. What if we had this? This is what we call an implicit function, because if we were trying to solve for y, as you can see, we have a squared here, so we would eventually have to take a square root. When you take a square root, there are 2 different answers that you get, right? A positive and negative. So this is an implicit function because of that. If we were taking the derivative of this, we're going to get something a little funky. I'm not going to completely do it, but let's just say we were doing ddx. Well, over here, we would get 2y. You still do the same. Doesn't matter, that's y. Except we have to add a y prime on there, because we're like, this was derivative of x. Since it's not derivative of y, we sneak in a prime there. So that's what you always do. If the dd something is not what variable, see these do not match up, then you add a whatever letter it is, prime, beside it. Over here, we do 2x. Why not 2x x prime? Because it was ddx, so we don't have to worry about that. Over here, that's just a 0. So that then, let's say you were trying to find y prime, you would just solve for y prime. So that's what implicit differentiation is. And one more example, and we'll see it later when we do look at related rates. We could do ddt, and that's like respect of time. If we were trying to do this, well, this time, this is going to be 6x. That's what it would normally be, right? If it was 6x squared. That's what it would normally be if it was ddx. But since it was ddt, we have to sneak in an x prime, because the t, it's not an x, it's a t. So that's what implicit differentiation is. It's actually not that hard. It just means if you're doing dd something that's not the same letter as what's in the equation that you're taking derivative of, you just sneak in a prime beside it. Higher derivatives. what I mean by this is sometimes, you might be asked to find, instead of just f prime, f double prime, f triple prime, or even something stupid like f 968. Now, how the heck would you do this? Well, sometimes it's easier than others, but it just means you do the derivative again. So if we had f double prime of x where it equals this, well, the first derivative is going to be 12x squared, right? Then you do it again, 24x. That's just what it means. But there can be sneaky ones. So let's say we had f 77. And you might also see this written differently. Like you could have something like this too. You could see it like that. Doesn't matter how you see it, whatever number you see, it tells you how many times to take it. Of sine of x. If you see something like this, it might seem so hard, but it's actually not. What you do is you try to find a pattern. Anytime you see a high number, you find a pattern, because there is no way you're going to want to do this 77 times. But if you can find a pattern, you'll know what it will be. So the first derivative we know is cosine x. Well, we know the derivative of cosine x is sine of x. The derivative of that is negative cosine x. The derivative of that is sine x again. So this was the first time we took the derivative, the second, the third, the fourth. And by the fourth, we're back to where we started. So this is considered a cyclical derivative, since it ends up back to where it was, but it takes 4 tries. So then we have to think 77. We have to figure out how that goes into 4. So we know, let's say 76 is, if we do 19 times 4, I believe that's 76, right? Yeah. So 76, that comes out evenly when you divide it by 4, right? We get 19. So that means 77 is going to be the same answer as what the first was. That might seem a little bit weird to think about, but just see how it is. You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and if we continued this on, we'd end up with 77 right here. And how we can know that is just figuring out, like I just did, okay, 76 goes into 4 evenly, or 4 goes into 76 evenly. So we know that 76 will be where it's back to normal, so then 77 is the next one, which is cosine of x. So the answer of this would be cosine x. So that's higher derivatives. All right, this next one is sneaky log problems. Now, if you'll just bear with me for a few seconds, I do want to pull up a problem for this one instead of just talking about it. Let's see here. I want to pull up an example, because this one's not going to be so easy to just talk about. I want to actually show you. Okay. All right. Okay. So the first thing that I will talk about what that means. This isn't an official term. Sneaky log problems, like I'll talk about what I mean by that in a second, and as a side note, if you're watching this, I really apologize if this is not high quality. I try my best with these videos, and I feel like that I'm kind of all over the place and kind of rushing through things. This is just supposed to be a review video. I wish I had the time to make every specific video in depth like I used to. Maybe I will do that one day, but this is really supposed to be a review, so I apologize that this video is so all over the place. But anyways, I hope it's at least making sense. So you're going to want to remember some log rules. So this is one what can we do to this? And this is just something that's reviewed from like Algebra 2 or however it was formatted in your high school. I do have videos on this. They might be from like 2021 though, but sorry about that. For this, you can do this. You can be like, yay, put that exponent to the side. So let's say we had this. We can say, there we go. We can do that. That's the first rule you want to know, and you'll see why in a second. I say that's good to know. The next is this. If you have two things multiplied within the ln or log, whatever it is, you can separate it by addition. The next is, let's say you have division. Well, you might have guessed it. Subtraction, yay. Now, pay attention to this part. If we have addition in here, you can't freaking do anything to that, sorry. And same thing with subtraction. If you have a minus b, can't do anything to that. So that's what you need to know. Now let's talk about what I mean by sneaky log problems. Sneaky log problems. These are problems where you see the derivative of something and it looks super stupid. Super stupid, and we don't want to do the normal thing we do. So let me give an example. So let's say you were asked to take the derivative of this. X to the power of sine of x. Well, in the first place, you might be thinking in your head, like, that's such a stupid function. Well, sorry, you might be asked something like this. And what could we even do right here? You might be thinking that. You might just be like, well, do I do the power rule? Do I do sine x times x to the power of sine x minus 1? Well, that doesn't get us anywhere, does it? That's not what we want to do. We will do something called logarithmic differentiation, and this is what I call a sneaky log problem. So let me just write that log diff for short. Logarithmic differentiation. That's what this process is that I'm about to do. Here's what you do. First, you do the ln of both sides. So we're going to do ln of y, ln of sine x to the power of sine x. Now we just say, okay, well, just leave that the same for now. But we're going to actually be like, okay, this stupid thing we'll put to the side using the log rule. So we're going to do sine x times ln of x. That looks a little better, you know, kind of. Then what we're going to do is, I'm kind of running out of room here. Oh, let's see here. There we go. Move that down. Now we can take the derivative of both sides. So we're going to just say d dx. I know that's not good writing, but we're doing the d dx both sides. Over here, this is where we use implicit differentiation. See this x, see this y, they're not the same, so we're going to have to do y prime. First, we'll just do this. What is the derivative of ln of y? No different than if it was ln of x. Instead of 1 over x, 1 over y. And we multiply that by, this is actually really the chain rule, kind of, sort of. What's in it, and the derivative of y for d dx is going to be y prime. Because they're not the same thing, right? Now over here, oh, wow. You might at first just be like, okay, cosine x times 1 over x. Yay, done. Oh, so sorry. Those are multiplied, and that means we have to do freaking power rule. Or sorry, product rule. We'll call this f, we'll call this g. I'll write my 4 things over here. Our f is sine x, our g is ln of x. The derivative of sine x is cosine x. The derivative of ln x is 1 over x. We'll do f times g prime. Plus f prime g. All right, now we want to get y prime by itself, so we divide by 1 over y. Guess what? That actually is the same as multiplying by y. So we're just going to say y prime equals, and that's going to be all of this. I'm not going to write that again. That's what would be in there. And you just multiply it by y, because, like I said, dividing by that is the same thing as multiplying by it. The reciprocal, which is just y. Now, your answer probably shouldn't be left this way because you can't have a y in there. So we'll just remember what I just did right there is all this. We'll replace that y with what the original question was. We see y equals x to the power of sine of x. So x to the power of sine of x. And that's your answer right there. That's logarithmic differentiation. And although that took a long time, that's way better than the other thing that we could have done with that. So you would want to use logarithmic differentiation whenever you see a function to the power of a function. So here's situations where you would not want to use logarithmic differentiation. Let's say we have 4 to the x. Not necessary. That's a number to the power of x. That's like the reverse thing. You don't have to do it there. Well, now we would. E to the x, obviously you know that's just e to the x. Wouldn't want to do it there. X, e to the x, okay, then you would. So you see what I mean? Only if it's a function to a power of function. You also might want to use it in a situation where it looks just really stupid. Like, I'll give an example. Let's say you had y equals e to the negative x times cosine squared of x divided by x squared plus x plus 1. Well, right here, you would have to do a lot of product rule, quotient rule. Ooh, that would take a long time. You could actually just simply do logarithmic differentiation, but it actually doesn't matter which one you do for this. So if you did product and quotient rule, that's fine. You can do whichever one you want. But for something like this, function to a function, that's pretty much your only option. So that's why it's good to learn this. Next thing we'll talk about is related rates. This is the one where I really do want to make a separate video on it because there's no point in me talking about it in this video in depth because this is very complicated. This is, in my opinion, the hardest thing. When we're talking about related rates, it's actually, and if you've been thinking so far that everything that we're learning is pointless, this is actually the time where you're like, okay, that can actually be used for something. So if we're talking about, let's just say we have, what's a good example? A common example you might see for related rates is, let's say there's two people that are at this red point. One starts walking this way, one starts walking this way. And it asks, how does the distance between them change? So we're talking about, that sounds like a derivative, right? At what rate does the distance between them change? If we had a question like that, that's very common. And a lot of times these seem so hard because it's like there's so many factors involved. Well, the first thing that I'm going to tell you to do is draw it. So that's my first step. And I'm going to make a separate video for this. That's guaranteed. We're going to draw that thing. So whatever it is, like I just said, there's so many endless possibilities of what they could ask you. Might not always be a triangle. They could say something about a volume of a sphere, volume of a cone, and hopefully they'll tell you that, at least for my purposes, the formulas will always be given to you. And we're going to talk in a second about how essential formulas are. So you're going to draw it. So let's just say, like I just said, okay, two people start at that spot. One goes west at a certain speed. One goes north at a certain speed. How does the rate of the distance between them change? Okay. Well, that's kind of a triangle, right? We have west, we have north. The distance between them, there you go. It's going to be the hypotenuse right there. So we draw it. Then we're going to say what we know. If you've ever watched my AP Physics videos from 3 years ago, whatever, you know I had a saying KNEF. That still applies here. KNEF. KNES, sometimes I referred to that too. It doesn't matter. That's a good acronym that's very good for word problems. You write what you know, you write what you need to find, you write what equations or formulas you'll use, and then you find what you're trying to do, or sometimes I would have it as a S, or solve. So KNES, we'll just say that for now, okay? That's the one I'll use. So you're going to write what you know. So for these kinds of problems, related rates, let's just say we had an x, y, and a z. That would make sense for a triangle, right? A, B, C, use any letters you want, but let's just say x, y, z. Might even put a theta in there if the question was asking about an angle. Then to the side, I'll write the exact same variables again, but I'll put little primes by them because we're talking about derivatives here. And the derivatives are going to be the change in these things. And this is just very basic. I'm going to have a separate video on this. But that's what we're going to do. We're going to write what we know. So let's just say we know this. I'm just making up random things here. We know this. We know this. We know this. And if nothing changes, like the angle's the same, we would label it as 0 because there's no change in it. Maybe then the angle's not even necessary for a problem. And then let's say you were trying to find z prime. That's the next thing. The n, you write what you need, saying the distance between them changing, that's going to be z prime. Distance between them is z, it changing it would be z prime. If you didn't know z, which is very common, there might be another one you don't know, well, we can use the Pythagorean theorem to figure that out. That's something that you won't be given, but I hope you know it. A squared plus b squared equals c squared. Just replace ABC with x, y, z, and you solve for z. And then what you do is you write the equations, and I just said for this purpose it would be the Pythagorean theorem. Then you solve, and how you would get z prime, any of these related rates problems, you take the derivative of the formula. So in this case, it would be this. And it's always with respect to time for related rates. Since that's the case, we do ddt. ddt on both sides. And this turns out to be 2x, right? X prime, how come? Tx, different variables. So we always have to have an x prime beside it. Next, 2y, y prime. Ty aren't the same, so we need a y prime. And then 2z, z prime. It's really good to put a dash through z's so you don't get confused with 2. And then essentially what you would do is you plug in all these values into this, and you solve for z prime. That's just algebra. So at the end of the day, these problems aren't really hard. The hardest part of it is knowing what everything in the question is. So what is this thing they just told me? Would that be the x? Would that be the y? That's why you draw it. So honestly, the hardest part would be coming up with this k. What do you know? This part right here. It's essential. What do you need? You need to know what the question is asking you to find. Then you figure out what formula to use. Hopefully they give it to you. But something as simple as Pythagorean theorem, or the area of a square, or the area of a rectangle, that's just something you'd want to memorize. But the volume of a cone, cylinder, I wouldn't be expecting you to memorize that. So if that doesn't make sense, please watch the video that I will make on that. But that's related rates. Linear approximations. This isn't too bad. It's not too bad. There's just one thing. You do need to memorize this formula I'm about to write. But what is the purpose of a linear approximation? This is if we're trying to find something that's, like, think about it. Like in the old days, they didn't have calculators. How could Isaac Newton determine what the square root of 818 was or something? If he was like, oh, 818. Like, how would he do that? Because there was no calculators in those days, right? This is one way, and then also Isaac Newton would use Newton's method that we're going to talk about later. So there's two ways to do it, but we'll talk about linear approximation first. The equation for finding a linear approximation, we'll say L of x equals f of a plus f prime of a times x minus a. Hey, guess what? This is actually very similar to point slope formula, which is just this, right? Now, how can we, for this purpose, we actually just take the y1 and we put it on the other side, so it's y1 plus. So essentially these two things are the same. These two are the same. And that's the same. So it's almost like a point slope formula in terms of derivatives. So that's a good way to remember it. If you have trouble memorizing what it looks like, just think it should look kind of similar to the point slope thing. So that means what you always have to do is find all these things. You need to know what f of a is, you need to know what f prime of a is, and you need to know what a is. Sometimes a will be given. So first of all, what the heck is a? Well, to understand this, let's just create an example of, let's just do what I said before. Square root of 818. Yeah, let's actually not do that because that's kind of too crazy. How about just a square root of 80? That's a little bit simpler. So you might be thinking, if before you knew what this is, you might just at least think, okay, I know that's going to be kind of close to 9, right? Because the square root of 81 is 9. But that's not good enough for the people in the old days. Like, if we're trying to, like, build bridges, that's not good enough to just be like, it's close to 9. Then we have, oh, goodbye bridge. So that's not good. So that's why we need to use this. So back to what we were saying. A, if what might A be? A, if we're choosing an A value, then A is going to need to be something that is close to this, what you're asked to find, and easy to calculate. So we can say, sorry, I'm trying to pull up a better example to see that. Okay, sorry. So we could say, all right, we'll make a square root of 82. That doesn't help us. It's close to it, but that doesn't, yeah, that's not good. So we can say, we're going to make a 9, because I know that that's close to 80, right? We could also just say a is the square root of 81. So that's how we choose our a value. Now we have to do f of a. So that means we plug this into the function. And you might say, hey, there's no function there. Well, you just make one. So the function for this would just be square root of x because that's what we see there. So we're going to plug a. So really what we would do is just 81. Plug in 81 into there. So I guess technically our a is 81. Sorry for the confusion, but a is just supposed to be something that we can calculate and it's easy, it's close to it. So we're going to say f of a is 9. F of a is 9. Now f prime of a, okay, what? You have to first know what f prime is. So we'll do the derivative of this, which is just simply this. Now we plug 81 into that. Okay, well, don't use a calculator because the point of this was to not. To the 1/2 that's negative, that's really going to be this. That's what this means. So that's going to be 1/9. 1/9 times 1/2 is 1/18. So f prime of a is 1/18. So then we would just, let me zoom out. We would just take this 1/9. So we just rewrite this equation over here and just plug everything in. 1/9 plus 1/18 times x minus a is 81. And this right here is known as our linearization equation. So we can plug any value in for x, and that should tell us, that will tell us what it is. Well, in this case, we wanted to do 80, right? That's what the question asked. So we're going to plug in 80. So we'd have 1/9 plus 1/18, and that would end up being -1. So it would really be this. Let's do a common denominator. So that's going to be 2/18 minus 1/18. And then I know we did something wrong right there. Because 1/18 I know is not close to 9, which is what our answer should be close to. Sorry about this. This is just so awesome when this happens, when you're improvising a problem and then you do something wrong. Let's just check our work here. I mean, this is good practice anyways to see what we did wrong. So let's first check on our f of a. So we ended up saying that was, oh, I know what went wrong. This was not the, I plugged in 1/9 for, that was the issue. 1/9 was not what f of a was. F of a was 9. 1/9, I was looking at that, that's not the right thing. So sorry, that's not what we do. Let's fix that. It's just going to be 9 minus 1/18. And shoot, that does get a little bit tricky, because how can we find a common denominator? That's going to have to be 9 times 18. So 18 times 9. 162. 162/18. So 162/18. So our answer is 161/18. So yes, that's not in decimal form, and there is a way to do this with oh, sorry, something was about to follow me. You know, long division, not going to do that. So they wouldn't need a calculator. But I will just type in this to see how close we were. 161 divided by 18 is 8.94 repeating. Okay, now I'll do the square root of 80. That is 8.9442. So the difference is, I said our answer with linearization was 8.9444 repeating. The actual answer to square root of 80 is 8.9442, actually rounding 443. So that's a lot better than us just saying it's close to 9. You see what I mean? So this got us closer. This is what they would do in the old days. Except it's still not that good, because you might say these are pretty close, but even that small amount of difference is enough to be something bad for like a structure or something. But that's linearization right there. That doesn't even matter. We're not doing something to build a bridge, right? This is just stupid calculus, right? So let's refresh what I did. You have to make this equation right here, and that's something you have to memorize. Remember, I say a good way to memorize it is know that it looks similar to the point-slope formula. So we had to find, what are the 3 things we had to find? We had to find A. Sometimes this will be given to you, but this time it wasn't, and I chose 81 because we know what the square root of 81 is, and it's close to the square root of 80. If I chose 64, that wouldn't be good, right? We know that's 8, but that's not close to square root of 80. And I didn't choose 79 because we don't know the square root of that. So that's what it has to be. It has to be something close to what you're asked and easy to calculate. So that's how we found A. Then we did f of a. So we had to plug that into the function. We didn't have a function, but we know this is what function we'll use. And when we did that, the answer was 9. Then we have to find f prime of a. That's the last thing. Well, that's kind of a double step because we don't know the derivative. We had to find the derivative, which was that. Then we plugged in 81, and we got 1 over 18. And so we plugged that in for f of a. So then we made our equation here. Not done. We plug in 80 to x because that's what we were asked to find. And the result was with our, like I said, we got 161 over 18. In the old days, if they really wanted to, they could have done this. I'm not doing that. I'm not doing that. And you don't have to do that either unless you have a professor that makes you. But don't have to do the long division. Just leave it as 161 over 18. And when I plug that into the calculator, this is what answer I got. This is the real answer. They're close, and that's the point of linear approximation. So I hope that made sense. Now there's another way to do it. Newton's method. Newton's method is more accurate, but it doesn't always work. So what the heck do we do for Newton's method? Well, I have a new thing for you to memorize. And it doesn't, also Newton's, like I said, Newton's method doesn't always work. So here's what formula you need to memorize. Okay, now you have to figure out what this means. So what is x2, what is x1? And that's what you might be thinking. Well, first of all, Newton's method is used to approximate zeros. So that's another thing. You can't use Newton's method for everything. Because not all functions have zeros. But let's just create a graph right here. Let's say we want to know what this 0 is, right here. x1, just like how, remember above, we chose 81 because it was close to 80. We're going to choose first something that we know. So let's say that this blue point right here was super easy to calculate. That's our x1. It's close to the purple, and it's easy to calculate. So this is x1. We would have to plug x1 into whatever function we have. So whatever this whole function is, we plug that into it, and then plug it into the derivative. So obviously you would also have to find the derivative. And if you're wondering how we get this function, it starts out looking like the rate of change, but I don't even need to talk about that. So once again, just memorize this. You don't need to really know how it's like this, but if it helps you, you can. But once again, there are 3 things we have to find x2, and I'll talk about what that means also in a second. But first of all, x1 is going to always be a value close to what you're trying to find, which is the purple. It's close, and it's easy to find too. So let's say this answer, whatever this is, the y value is 7. That's good. That's a whole number that's pretty good. If it was like 7.536, that wouldn't be very good. Or if it was over here, that also wouldn't be good because it's closer to this 0, so we would end up getting the wrong answer. So then you plug whatever that is into the function that you're given. Then you plug it into the derivative that you'll have to find. Do this, and that gives you x2. What is x2? x2 is going to be our next value that's close to... So essentially what we're doing is this. So let me just choose color I haven't done. So this blue, we're going down here, or we're choosing, okay, so this is on the x-axis, we're going up to the graph. So let's say x1 was 6. This would be 6 right here. We're going up to here to the graph, and we're creating a tangent line. And that takes us, I know that's not a straight line, to here. This is our x2. So this was x1. This is x2. We go back up to the graph. We make another tangent line. This is, yeah, maximum. It won't let me zoom in anymore. Let me try to draw it better because that's not really good. Oh, shoot. I'm sorry. This thing does not work very well always. Okay. I don't even need to do a full thing like that. Let's just only have one quadrant. So, okay. So this is our function. We are trying to find, let's just go back to that purple color again. This is what we want to find. So we choose an x1 that is easy to find. Let's say that this is what we choose as x1. And the reasoning that we would do that is, let's say whatever this y value is right here is a whole number. Let's just say it's -3. It's easy to calculate. Because there's no point in doing like something like this. That's not easy. So we find out something that's close and easy. We don't want to do an x1 right here because that's going to make us end up figuring out that 0. So then we sneak down here using that formula that I told you, and we're going to do the tangent line right there. So tangent, this is not really a good example, honestly. I'm sorry. Let's just do something more like this. That's kind of better. So the tangent line right there would be something like I'm trying to just choose an example that's at that point. Let's just say that the tangent line is there. This becomes our x2. Then we go right back down here again, tangent line again, x3, and we get closer and closer and closer until we finally get to it. That's what Newton's method is visually. You need to know that, but you also need to know how to use this equation. So you don't need to only know it graphically. So I hope that makes sense. I'm sorry that was like I had to change it up. I was just trying to make it visually look easier. But essentially what we're doing is we're just finding an x-intercept, then we're finding the tangent line of that, going again, 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 again. So x2 in this situation would be our next x-intercept that's closer to what we're trying to find. Then we'll do a 3, and then we'll change these to 2s. To find the third one, we'll do 4, and we'll change these to 3. So it's just a continuous process you could do infinite times, and you get closer to 0. Closer to the 0 you're trying to find, closer to the x-intercept, however you want to call it. This is Newton's method. Newton's method doesn't always work, like I said. Let's talk about why. I already mentioned briefly one example of why it wouldn't work. So let's say we do this. We're trying to find this. We go right here. We're going to end up getting tangent lines that take us, that's not drawn correctly, but we're going to end up getting tangent lines that take us to this x-intercept instead. That's where it can fail. So that just means you have to choose a better value that's closer to it. Newton's method might also fail if you have something like this, a slope of 0. So if we do it right here, that gives us a dead end because the tangent line's like that and it never gets back up to the x-axis. Because that's what always is supposed to happen. When we do a tangent line, when we find the tangent line, it's supposed to take us to another x-intercept. Well, this doesn't. It just, if the slope's 0, then that line doesn't go to the x-intercept or x-axis. Another reason why it would fail is this. That doesn't even go through. There is no 0. And then there's a fourth reason, which is kind of hard for me to draw, but there is some examples of graphs where maybe like this, where it would just take you back and forth. So if you do it right here, maybe that's not good. So if you do, let's just say, okay, let's choose this point. Okay, well then that's going to be like, okay, then we do, it's a hard, it's a hard thing for me to draw visually, but essentially it would fail if you end up having something where it goes back and forth, and that can happen. Let me see if I can find a better example. I'm sorry. I don't know. I'm not seeing that good of examples, but essentially sometimes maybe I can draw this better. So we have something that looks like this. Okay, we choose this. It's going to go like this. And then that one would go up to here, and then it's going to go like this, and then it's like that. It would just go back and forth, and it would never take us to either of these zeros if we were trying to find it. So that's the next and final reason that I'm going to talk about of why Newton's method would fail. Okay, and that is it for this video. It was a long video, as probably expected. But that's all of the content that's in this unit. And I'm going to briefly review everything in case you forgot, okay? Because it was a long video. And once again, I will make a related rates specific video because that was not possible for me to talk on here. So remember, we start out by saying you sometimes have to use this formula right here to find limits or find derivatives. And all you have to do is plug in for f of x what it is, and for f of x minus h, whatever the function is, but anywhere you see an x, you replace it with x minus h. You solve, and basically the value, you're going to end up wanting to cancel out that h in the bottom, right? Because if you plug in 0, right, h of 0, you're going to get denominator of 0. So you have to cancel out that h. It will work. If they give you a problem, it's going to work. So just keep that in mind. You're trying to cancel out that bottom h. And then you would get your derivative that way, if that's the way that you're asked to do it. And if you needed to find the tangent line, you use the point slope formula. The x1 and the y1 are given to you. X and y, you don't change. Okay, that's just what it is. x1, y1, they'll be given. M, you find by whatever the derivative was, and you plug in x1 for x into the derivative, and that gets you your value m. Next, if something's differentiable, it means you're able to take the derivative of it. Essentially, that's what it means. And you only can if there's no corners, cusps, vertical tangent lines, meaning that the graph goes vertical, so it kind of looks like this. That's not something you can do right there. And the slope needs to be the same on both sides. If it's differentiable, it must be continuous, but if it's continuous, it's not always differentiable. Basic derivatives, I'm not going to go over that again, but keep in mind, most of them are pretty easy to remember, but the ones you'll want to memorize chain rule, product rule, quotient rule, power rule. Those are the 4 rules. You want to memorize e to the x is just e to the x. You want to know ln of x. You want to know log of x. You want to know all 12 trigonometric ones, the normal and the arcs. The c's are always negative, remember what I said? You want to know derivative constant, always 0. Implicit differentiation, if you take the derivative of something with respect to a different letter, like for example d dt, there's always going to be a prime multiplied by the derivative of what you took. So d dt of x squared would be 2xx prime. Higher derivatives, you just do it over and over, and you might be able to find a pattern like we did for this. Sneaky log problems, if you have a function to a function, only for that. Or something like, is it still here? Yeah, something like that where it's kind of stupid. It's optional. You could do logarithmic differentiation, but especially if it's a function to a function, you ln both sides. Remember your rules, you can make the exponent go beside it. And then over here, if we were to use logarithmic differentiation, we would end up seeing that we would have log of something times something, which you would separate it by addition. And then you'll have to probably use product rule if you do this. And then remember that you have to get y prime by itself and don't leave it as y. Replace it with what y equals. Related rates, I'm going to make another video on that. I'm not going to talk about that. Linear approximations, we use this equation to determine numbers that we can't know just off the top of our heads. Square root of 80. Newton's method, same thing. You could also use that to find a value you don't know, but zeros are what you have to do. Graphically, we are just creating tangent lines and getting closer and closer to what we're trying to find. Sometimes it can fail if there's something that goes awry. And there you go. That's the end of this video. I hope it helped, and stay tuned for the related rates video.